All right, so we can see here then if we had a little pin on our mass and we had a piece of paper rolling out from under the mass as the mass moved up and down with simple harmonic motion, the kind of curve that we just expressed would be drawn out. And so this, again, is not a wave that we're drawing here, but is the displacement as a function of time for a simple harmonic oscillator. Now, here are examples of x versus t plots for different frequencies. Okay, and so we'll get into what causes the frequency of the motion and therefore the period to change in a few minutes. But this x versus t plot does define the period and therefore the frequency of the motion. And if we're talking about the same mass and spring system, then it can have different maximum amplitudes while still having the same frequency of motion. So this is essentially what I drew on the board a few minutes ago. Now here are some other examples of simple harmonic motion. A marble in the bottom of a bowl is one that we haven't talked about so far. Also the oscillation of a molecule like oxygen, O2, vibrating back and forth with a huge number of oscillations per second. In this case, we might be talking about 10 to the 13th power cycles per second, or 10 to the 13th power hertz. And so this is kind of amazing that these systems can have such large frequencies of oscillation associated with them. And so here, what I want to do next is take a look at, if we know what the cosine omega t curve looks like, then we should be able to derive expressions for the velocity and the acceleration of the mass as it experiences simple harmonic motion. So I'll do that now on the lower board. If the x versus t looks like this, and this is x equals a cosine omega t, then the velocity, v, would be dx dt. So that would be, well, we'd have the derivative of cosine is minus sine times the derivative of the inner function, using the chain rule, that would be omega. So it would be minus omega a times the sine of omega t. And so the velocity versus time would look like a minus sine function with a maximum amplitude that's equal to plus or minus omega a. Okay, so when would the object have the maximum negative velocity? Well, that would occur when the mass has been released from rest from its maximum equilibrium position, x equals a, and has reached the equilibrium position, because at that point all of the potential energy would have turned into kinetic energy, but the velocity would be negative. And so that's what we would have down here. And the maximum velocity in terms of its magnitude would be equal to 2 pi over the period, or omega, times our original value for a. And so then when the velocity is 0 would be at the points here where the displacement was a maximum. Okay? And so that would occur then when we reach this point, and when we're at that point the velocity is 0. That corresponds to the x value being its maximum possible value. And then the acceleration a, we can plot over here. A is dv dt. So a versus t that would be the derivative with respect to time of minus omega a times the sine of omega t would be equal to, well, we get another factor of omega derivative of sine is cosine, so it'd be minus omega squared a times the cosine of omega t. But this is just minus omega squared x, because if you'll recall, x is equal to a times the cosine of omega t. So what we end up with then is basically just the plot of a negative cosine function with a maximum value of minus omega squared x. Okay, and so this would be a max, so this would be omega squared a, and this would be the maximum negative value for the acceleration minus omega squared a. And so that would occur when the x values are at their maximum, but here, when the x value is at its maximum, the acceleration is negative. And here, when the x value is at its negative value, maximum negative value, the acceleration would be positive. And so it would differ in phase by 180 degrees from the x versus t plot, but of course you'd be plotting something different. You'd be plotting acceleration rather than plotting displacement. Okay, so the next thing that I wanted to look at is, with these relationships in mind, how do we define omega? Because everything seems to be in terms of omega and our maximum amplitude. And so how do we define that? Well, we go back to our basic equation for the restoring force, F equals minus kx. And so you might say, well, wait a minute, this was only the restoring force for a mass spring system. What about our simple pendulum? Well, the simple pendulum and all of those other expressions that we looked at can be put in this form with an equivalent spring constant. And so even though there's not a spring in those other problems, we can still treat them mathematically as if there were. And so that means that with no loss in generality, I can write the expression here for omega in terms of the spring constant. And then if I wanted to, in one of these other problems, like the simple pendulum problem, I could go back and find the equivalent spring constant, say, for the pendulum. And also for masses that are vibrating, the force in that case is an electrostatic force. It's the force of attraction and repulsion between protons and electrons. If we're talking, say, about the vibration of that oxygen molecule as it goes back and forth, or the vibration of atoms in a crystal. All of those kinds of vibrations can also be thought of in terms of an equivalent spring constant, even though there's no real springs there. We're just dealing with forces of attraction and repulsion that approximate our linear restoring force for a mass spring system. Okay, so with that thought in mind, we can rewrite this as mass times the second derivative of displacement, because here we've got displacement on the left. So we would want to write our force in terms of the same quantities that we have on the left and the right. And then, simple enough, this looks kind of nasty, but if we just write now x equals a times the cosine of omega t, take two derivatives of it and plug it in here, we get a condition on omega that allows for the solution to be valid. Okay. And so let's do that. Let's take the derivative first of x. Well, we've already done that. That's minus omega a times the sine of omega t. And then the second derivative of x with respect to time squared, that's just dv dt. That's minus omega squared a cosine omega t, or minus omega squared x. So we know how to do this already. We did this just a second ago. So mass times minus omega squared x equals minus kx. The x's cancel, and so omega squared equals k over m, or omega is equal to the square root of k over m. So now we have an expression for omega. If we know what the spring constant is and what the mass is, we can just plug those values in and we can get an expression for omega. So let's do that. Let's say that we know that the spring constant is 10 newtons per meter for a given problem, and the mass is 100 grams. Or 0.1 kilograms. Then omega would be the square root of K over M, 10 newtons per meter, divided by 0.1 kilograms. And so that'll give us square root of 100, or that would be 10. And the units for omega are the same as the units for omega were before, when we were doing this with a simple, with circular motion, where omega was equal to our angular velocity, and that has units of radians per second still. So omega has units of radians per second. Now why is that equal to 2 pi times the frequency? Well, because omega, the units of radians per second, and frequency has units of cycles per second, or hertz, then we have to convert from cycles per second to radians per second. And so that's going to be 2 pi radians per cycle. So we have 2 pi radians per cycle times cycles per second gives us radians per second. And so it's that simple. It's just a conversion factor that converts from radians to cycles. And that's why omega is equal to 2 pi times the frequency. So this is something I didn't fully understand when I was first learning this. So I just memorized it. But this is your working equation for being able to convert back and forth between omega and either frequency or period. Okay, so once we know what the omega value is, we can immediately get the frequency. The frequency for this problem would be omega over 2 pi, which would be 10 divided by 6.28. So the frequency then would be somewhere between 1 and 2 cycles per second. .58 hertz. And the period would be 1 over the frequency, easiest way to do it at this point, and that would give us 0.628 seconds. So once we have omega, it's easy for us to find the frequency and the period. And the omega value that we have for this particular problem is the square root of K over M. Okay? And so let's say that in our next example, we have a car that is moving along, and it has support structures that could be modeled as 4 springs. So here are 4 wheels on the car. Each one, let's assume, carries an equal load, so that the center of mass of the system is in the geometric center of the car, equal distance away from all 4 springs. And let's say that the spring constant for this problem is equal to 20,000, which is more typical of the spring constant for something that's carrying a very big load, like a car, maybe 20,000 newtons per meter. Surprisingly, though, when we work out the spring constant for a molecule, it has a similar value. And so that's kind of amazing. But remember that the omega is the square root of k over m. And so with a huge value for k, even though you're taking the square root of it, that's what gives you such high frequencies, like 10 to the 13th power cycles per second. And so it's very strong restoring forces in molecules as well as in really big objects like cars. And so let's say that this car is moving along a road without shocks. And unfortunately, I found myself in this situation once. I had taken the shocks out of my car, and then I couldn't get the other ones in. And I had to move out of the house and go to school at UC Santa Barbara. And so I was getting kind of frustrated. I already had everything piled on that I owned in the car. And I didn't want to take all that stuff off. I was afraid there was maybe too much weight. That's why I couldn't get the shocks in. But I said, who needs shocks anyway? And so I started driving up without them. And so the mass of the car, I would guess the total mass with me in it and all my stuff, let's say 2,000 kilograms. And then I started hitting these bumps in the road. I was driving north towards Santa Barbara from Los Angeles, and I was on Highway 126, and I started hitting these bumps, and the car started going crazy because I was stimulating the system at its natural frequency of vibration. And I was hitting these bumps at something like 1 time a second. Okay? I was going about 60 miles an hour, and the vibrations went all over the place. And I wasn't sure what to do. I didn't know as much as I know now about simple harmonic motion. But I did know that I had to break up the pattern. There was a bad pattern. And if I kept going with that pattern, I was going to die. And so I started speeding up and slowing down. And it was very upsetting experience, but I was able to maintain control of the car. I got it up to Santa Barbara. First thing I did was pull into a gas station. I go, would you please put these shocks in for me? And they go, sure, I'd be glad to. And so everything was fine from there. But for this problem, let's find the natural period and the frequency for the system. Okay, so omega then is going to be equal to the square root of k over m. But this would be true for each spring. And so the mass that I'm going to want to plug in here, think about this for a second. Since the springs are each supporting 1/4 of the total weight, the effective mass on each spring is just 1/4 of the total mass. And so therefore, this is going to be a different, it'll be the same value, but it'll be an independent value for omega for each of the 4 tires. So there actually will be a slight phase differential between the two that we don't need to worry about here. We'll write this as the square root of 20,000 Newton per meter divided by not 2,000, but 2,000 over 4, or 500 kilograms. And so that is the effective mass that's weighting down each spring. And so then, if we punch that number out, that's going to be the square root of 20,000 divided by 500, so that would be 40 square root is 6.32 radians per second. Remember that anytime we're dealing with omega, we're dealing with units of angle per time. Remember over here, cosine omega t, radians per second times seconds. So that gives us units of radians. So that's what omega has to be in terms of, and your calculator has to be converted over to radian measure before you can take the cosine of that angle. Okay, and so, but we're not quite done, because we need the frequency in the period. So the frequency is omega over 2 pi. So that's 6.32 divided by 6.28. So that gives me a little more than 1 cycle per second. .007 hertz. And then the period would be equal to 1 over the frequency. So that would be 0.998 seconds. So this is about what I was feeling. I was feeling like I was hitting these bumps about 1 time per second. And that's what was causing the resonance. Because if I can add energy at the natural frequency of motion, that vibration will get bigger. And the same thing is true with any kind of a system that is experiencing simple harmonic motion. I could take this simple pendulum, has a certain frequency, and then you could start to push it at that frequency. You can see what happens. We're resonating with the system by adding more energy in than is being lost during one complete cycle. And we resonate with the system, causing the amplitude to grow essentially without limit until the system goes flying apart. And so that same kind of thing can happen with buildings too. Buildings have a natural frequency of vibration as they vibrate back and forth. And so just any kind of a mass can reproduce this result. Here, set it like this. See that kind of vibration. But it would be vertical, so it would be vibrating back and forth like that. That could be a building. And so if an earthquake then excites that natural frequency of vibration, then the building can collapse. And so this is the reason why the Japanese have been able to develop systems in which they've got masses that move to counteract the vibration of the building. And as the building sways one way, the mass will move in the opposite direction to cancel out the seismic vibrations. And so this is particularly important in Japan because they get a huge number of earthquakes there. And, but they're very inventive and have been able to figure out a system that helps to mitigate this problem. There are instances in World War II of soldiers marching across bridges. And those bridges would collapse because the rate at which they were adding energy to the system matched the natural resonant frequency of the bridge. And they didn't have enough common sense to realize that before the whole bridge had collapsed. And so now, standard operating procedure when you're crossing a bridge is to never march in step.